I am Mandapure. My IT number is IT2319480. So let's talk about FPGAs for parallel processing in clusters. What is an FPGA? First of all, we'll talk about that. FPGAs or field programmable gate arrays are reprogrammable semiconductor devices. Unlike CPUs, which have a fixed architecture, FPGAs can be configured after manufacturing to perform specific tasks. This makes them highly flexible and specialized. So how these FPGAs can be enabled to do parallelism? FPGAs enable parallelism by executing many operations simultaneously using dedicated hardware circuits unlike CPUs that process instruction sequences. FPGAs rely on reconfigurable logic blocks tailored for specific tasks, resulting in very low latency and more power efficient processing for parallel workloads. Just as I shows in this presentation, uh, the execution times, architecture, flexibility, latency, performance, power efficiency are almost different in CPUs and FPGAs. So why we use FPGAs in clusters? In cluster computing, FPGAs offer reconfigurable hardware custom design for particular applications. They execute multiple operations simultaneously at the hardware level, providing lower latency and higher power efficiency than CPUs, which work sequentially. This results in reduced power consumption without sacrificing performance. With applications in data centers, signal processing, finance, and genomic research. So these FPGAs have both strengths and weaknesses. First, we'll talk about the strengths of these FPGAs. We'll talk about mainly customizable for specific exploration, low latency and high throughput, and deterministic behavior for great for real-time systems. So FPGAs provide several key strengths, as I told before. They are customizable to specific applications, so eliminating unnecessary components to improve speed and efficiency. And also, they deliver low latency and high throughput by executing operations directly in hardware. And furthermore, as I told earlier also, their deterministic behavior makes them ideal for real-time systems like autonomous vehicles and medical devices. Next, for the weaknesses of FPGAs. Even though they have strength, they have some limitations, such as programming them requires a knowledge of hardware description languages like VHDL or Verilog, which have a steeper learning curve compared to other software languages. Their development time is longer due to the need for design, simulation, and hardware validation stages. Additionally, FPGAs typically operate at lower clock speeds than CPUs. They have limited performance in sequential or single-threaded tasks. So if we took some real-world examples, many leading organizations have adapted to FPGAs, such as Microsoft Azure uses them for real-time search acceleration, and Intel combines Xeon CPUs with FPGAs to create hybrid AI systems. And also CERN employs FPGAs in particular detectors for data filtering. Next, these are two recent developments, Xilinx Versal AI Core and Intel Agilex FPGAs. So, Xilinx Versal AI Core, which integrates traditional FPGA fabric with dedicated AI engines and DSP blocks for high-performance AI workloads. And also Intel Agilex FPGAs, built on advanced 10 nanometer processors, offer higher logic density, better power efficiency, and support for technologies like PCLE Gen 5 and high bandwidth memory targeting (HPCs), AI, and cloud workloads. So, as the summary of the things we discussed until now, FPGAs are reconfigurable devices that deliver hardware-level parallelism with low latency and power consumption. They are highly customizable and used widely in HPC clusters, AI acceleration, cloud data centers, and telecommunications. So, these are the references that I have used in order to uh, make this presentation. And this will be the end of my presentation. Thank you.